just complain.
Okay, let's start again. Our next talk is also conventional, and the speaker is Youichi Yanase. Talk about generation, modulation, and enhancement of superconductivity by quantum geometry.
Okay, so thank you very much for the introductions. First of all, I'd like to thank the organizers for giving me this opportunity to speak about our recent study on quantum geometry in superconductors. So it is my pleasure to present in one approach. So my name is Youichi Yanase. I am from Tokyo University in Japan. So I suppose that so many people in the audience is expert for the quantum geometry, but I'd like to begin my talk with reminding you the quantum geometry in quantum physics. So actually, the quantum geometry is closely related to the topologies. While the topology represents the global structure of the object, right? So on the other hand, the geometry represents the local structure of the object, so such as the curvature on the surface of the donuts. But these two concepts are closely related to each other. Indeed, if a person goes around on the surface of the donuts, so probably he will notice the presence of the holes in the donuts. So in this case, in this sense, the geometry is an origin of the topology. So this is also the case of the condensed matter physics. So maybe you know the number, so which is a typical topological invariant in the condensed matter physics, and it is obtained by the integral of the very curvature in the brilliant zones. And the very curvature is one of the geometric quantities which represents the geometric structure of the band structure. But okay. So in the quantum matter physics, so we usually consider the geometric properties in the momentum space. So then the quantum geometry is defined by the momentum dependence of the Bloch wave functions. So as discussed by the previous speaker, Professor Rowe. Okay. So here I am showing the eigenvalue equation for the Bloch electrons, and you see the energy dispersion here. So by which we can calculate the group velocities and the effective mass. We are very familiar to the physical phenomena related to these quantities, so such as the conductivities, and superfluid. So, but on the other hand, not only the energy dispersions, but also the Bloch wave function depends on the momentums. So that's determines the quantum geometry. So actually, so we can define the very curvature through the momentum derivative of the Bloch wave functions like this. So this corresponds to the quantum geometries. So similar to the going around on the surface of the donuts. Okay. Okay. So we are very familiar to the physical phenomena related to the very curvatures. So actually, so many people have clarified the several phenomena closely related to the very curvatures. But probably one of the most typical example is the intrinsic conductivities, which is obtained by the integral of the very curvature for the occupied state. And it is quantized by the Chern number as in insulator at the temperatures. So this is nothing but the quantum effect. So, but here, so I'd like to emphasize that the very curvature does not represent the whole band geometries. For instance, the quantum geometric tensor is defined like this, and here we see the imaginary part, which is nothing but the very curvatures. But in addition to the very curvatures, so we can see we also have the real part, which is called Fubini-Study quantum metrics. So now here the question is the following: what is the role of quantum metrics in the condensed matter physics? So actually, the effect of the quantum metrics has less intensively studied in the condensed matter physics compared with the very curvatures. But recently, as well, people studied the role of the quantum metric in nonlinear optics, nonlinear transport, multipolar moment, and also there are random levels. So, but the question for myself is the effect of the quantum metric on the superconductors. So, what is the role of the quantum metric on the many-body quantum state in superconductors? So, but it is reasonable to expect that the quantum metrics is also important for superconductors because the quantum metrics have a clear physical meaning, as explained by the previous speaker, Professor Rowe. So it is closely related to the quantum distance. Quantum distance is represents the difference between the two quantum states. So, and in the momentum space, the quantum matrix obtained by the second order derivative of the quantum distance like this. So we can expect to see the quantum matrix in superconductor as well. So actually, in these years, so my research groups have investigated the superconducting phenomena related to the quantum matrix. And in this talk, I'd like to talk about three topics. The first one is the generation of superconductivity. So namely the spin-triplet superconductivity induced by quantum geometries. And the second topic is the enhancement of superconductivities. So namely the enhancement of the BKT transition temperature in monolayer ion cyanide. And the third topic is the modulation of superconductivities. So where I will discuss the possibility of the finite-momentum superconducting state stabilized by the quantum geometry. So, as shown by the author of our papers, the main player of our study is Taisei Kitamura. So Taisei Kitamura is a PhD student in my groups. And another important player is Professor Akito Daido. So he is an assistant professor in my research groups. Okay, so let me move on to the first topic. So that is the spin-triplet superconductivity induced by quantum geometry and so related to ferromagnetic spin fluctuations. So I'd like to begin this part with reminding the spin-triplet superconductivities. So spin-triplet superconductivity has attracted much attention because it is a platform of multiple superconducting phases. And it leads to the spontaneous symmetry breaking, such as the time reversal symmetry breaking or rotation symmetry breaking. And more recently, the spin-triplet superconductivity is attracting much interest because it is a platform of the topological superconductivities. But however, the candidate materials for spin-triplet superconductivity is very rare in nature. So that is probably because the effective interaction in the strongly correlated electron systems favor the spin-singlet superconductivity in most cases. And it is well known that the ferromagnetic fluctuation is a canonical origin of spin-triplet superconductivities because the ferromagnetic spin-spin correlation favors the spin parallel Cooper pairs. But unfortunately, candidate materials for ferromagnetic spin fluctuation induced spin-triplet superconductivity is very rare. So as we can see, most of them in heavy variable superconductor, such as uranium javelin and uranium diatomite. So actually, so my research group is also interested in these heavy variable superconductors, and we are working on this. But it is better to have other candidates as well, and we will be very happy. So if we have a guiding principle for searching the spin-triplet superconductivities. So in this talk, I'd like to propose a guiding principles based on the quantum geometries. So let me explain my idea. So in the following few slides, so I'd like to I will focus on curvature of spin susceptibility in the momentum space. So this is related to the spin ferromagnetic spin fluctuation and anti-ferromagnetic fluctuations. So when the curvature of spin susceptibility in the momentum space is negative, we have a chance to see the ferromagnetic spin fluctuations. So however, when the curvature is positive, the ferromagnetic spin fluctuation is ruled out, and the spin fluctuation must be anti-ferromagnetic. So, let me discuss the curvature of spin magnetic susceptibilities. So here, so I am showing the formula of spin susceptibility of free fermions in multiband systems. So here we see the quantum distance. So by this formula, we immediately notice that the quantum distance always favors the ferromagnetic fluctuation rather than the anti-ferromagnetic fluctuation. So this is because the quantum distance must be positive, and it disappears at Q equals 0. So this means that the quantum distance suppresses the anti-ferromagnetic fluctuation and leading to the dominant ferromagnetic fluctuations. Okay. So in order to formulate these ideas, so we calculated the curvature of magnetic susceptibility in free fermion systems, and it is obtained like this. So we have two terms. One is coming from the conventional ferromagnetic term, conventional ferromagnetic stories, and this term is mainly determined by the nesting properties of the Fermi surfaces. But in addition to these conventional terms, so we obtained the quantum geometric correction to the curvature of spin susceptibilities. And this term is furthermore divided into the two terms like this. But consistent with our naive expectations, we can see the quantum metric here. So in the first term of the quantum geometric corrections. And we can say that this quantum metric term always favors the ferromagnetic spin fluctuation because this term must be negative. On the other hand, we also have a second term here, which is related to the positional shift of Bloch electrons under the electric field. So we call this term the positional shift terms. So unfortunately, this term always favors the anti-ferromagnetic fluctuations. So therefore, the quantum geometric correction to this spin fluctuation is determined by the competition of these two terms. So but anyway, so to see the sizable contribution from quantum geometries, so it is better to consider the system with band degeneracy because the quantum geometry is usually enhancing in the presence of the band geometries. So let me consider the system with band degeneracies. Okay. But I'd like to mention that the canonical Dirac electron systems, such as graphene or KMR models, are not suitable for our purpose because, so according to these terms, the quantum metric term is a Fermi surface terms. So in the absence of the Fermi surface, the contribution from quantum metric disappears. So from these results, so we expect that the topological metal with large Fermi surfaces, so maybe a platform of ferromagnetic fluctuations induced by the quantum geometries. Okay, so to verify these expectations, we studied a model for the topological metal. So that is the extended Riemann lattice model. So probably the Riemann lattice is well known as a canonical model for the flat band systems. But in our models, the flat band our model does not have a flat band because we take into account the long range hopping as well. So here I am showing the dispersion relation of the model. So actually, so we avoided to study the flat band systems because we would like to distinguish the ferromagnetic fluctuation due to the quantum geometry from the flat band ferromagnetism. Okay, but anyway, so even in the presence of the long range hopping, the band degeneracy is robust in this model because the band degeneracy is protected by the four-fold rotation symmetry. So when we set the Fermi level so at the Dirac point here, so we obtain the Fermi surface like this. So in this case, we can see the large Fermi surfaces connected at the Dirac point here. So consistent with our expectations, the quantum geometric correction to the curvature of spin susceptibility is negative in this case. It mainly comes from the momentum space around the other. That's okay. Okay, I'm sorry. Can I stop? Yeah. So I mean, the quantum geometric correction to the curvature of spin susceptibility is largely negative, as it comes from the momentum space around the Dirac point, as shown here. I need to change the line for it. Okay. So now we have ferromagnetic fluctuations. So here I am showing the chemical potential dependence of the curvature of the semi-susceptibilities, and it shows large negative peaks around the Dirac point. So this means that the band degeneracy gives the ferromagnetic spin fluctuations. So consistent with this fact, so we obtained the momentum dependence of the magnetic susceptibility like this, and it shows it actually shows a big RK quarter here. So on the other hand, so when we neglect the quantum geometries, we obtain the momentum spin, we obtain the spin susceptibility like this. It's in these figures. So we see that the ferromagnetic fluctuation disappears as we see the large peak around pi. So this rather means anti-ferromagnetic fluctuation. So this means that the ferromagnetic fluctuation is induced by the quantum geometry in this case. So finally, so we studied the superconductivity in this model. So when we take into account the Coulomb interactions, so by using the random phase approximations, the ferromagnetic spin fluctuation is significantly enhanced like this. And by using these spin fluctuations, we evaluated the superconducting instabilities by solving the area symmetric equations. So here, I am showing the chemical potential dependence of the eigenvalue of the area symmetric equations. We can determine the leading instability of superconductivity by looking at the eigenvalues. So this figure shows that the in this figure, so we see a large peak for the spin-triplet P-wave superconductivity here. So this appears when the level is close to the Dirac point, as we expected. So I mean, so the take-home message of this part is the following. So the topological metal, so with large perimeter surface and strong electron correlation, may be a platform of spin-triplet superconductivities. So this is our proposal for the guiding relation for searching the spin-triplet superconductors. Okay. Maybe 5 minutes. 7 minutes. 30 minutes. Okay. So maybe I have still time to talk about the second topics. So that is the enhancement of the BKT transition temperature in nuclear area. So I'd like to begin this talk with introducing pioneering work for quantum geometry in superconductors. So it was given by Sebastian Feosta and Professor Tarman in Aalto University, Finland. So they formulated the superfluid wave. So in the S-wave superconductors of multi-band systems. And they found that the superfluid weight is determined by the two terms. The one is described by the conventional perimeter theories. And in addition to these terms, they obtained the correction from the quantum geometries. So these terms. And the correction to the quantum geometric term for the superfluid weight is generally represented by the boundary resolved quantum metric like this. But when we consider the isolated band limit, where the energy bands are energetically separated from each other, so then this term is reduced to the quantum metric like this. Interestingly, so they also found the topological band for the superfluid weight arising from the quantum metric. So because the quantum geometric tensor has a semi-definitive properties, so we can show that these terms must be rather than the absolute value of the Chern number. So this is the topological band. That means phasor band has phasor band is topologically non-trivial and characterized by the finite Chern numbers. We will see the finite contribution from the quantum metric in superfluid way. And furthermore, so they consider the flat band systems where the conventional periodic term completely disappears. So because the effective mass diverges in the flat band systems, the superfluid weight is completely determined by the quantum geometric collections, and it is bounded from below by the Chern numbers. So this is the reason why the title of their paper is Superfluidity in topologically non-trivial flat bands. Okay, so after their theoretical studies, several people studied the superfluid weight in flat band superconductors, so, such as Lee practice and twisted wire graphens. And consistent with the pioneering works, they found that the quantum geometry dominates the superfluid weight in these systems. Okay, so but I have several questions. The first question is that is the flat band necessary to see the quantum geometry in superconductors? So this is the first question. And second question is the real materials other than the flat tensor barrier graphene. So to answer these questions, so we studied the superconductivity in monolayer iron selenide. So this compound was intentionally studied because it shows a high temperature superconductivity. So although the transition temperature of bulk iron selenide is less than 10 kelvins, so the transition temperature of monolayer iron selenide was reported to be around 60 Kelvin or 80 Kelvin. So this is high temperature superconductors. But probably so these temperature are not the real transition temperature because the zero electric resistance was observed at a much lower temperature, around 60 Kelvin. So this means that the superconducting transition is determined by the BKT transition characteristic to the two-dimensional superconductors. So actually, this is a purely two-dimensional superconductors. So, and it is reasonable to consider that this transition temperature is related to the superfluid weight, because the BKT transition temperature is determined by the so-called Nelson-Holstein relation, as shown here. So to evaluate the contribution of quantum metric to the superfluid weight and transition temperature in monolayer iron selenide, so we derived the generalized formula of the superfluid weight in unconventional superconductors. So because the momentum dependence and band dependence were neglected in the previous theories, we extended the formula to take into account the unconventional properties. And we found that the superfluid weight can be decomposed into the 4 terms like this, and 2 of them have geometric constant. So to evaluate the quantum geometric contribution to the superfluid weight in monolayer iron selenide, so we carried out the first principle band structure calculations and derived the effectivity of the models. And by solving this model with using the amended BCA theories, so we evaluated the superfluid. So here, we have studied several superconducting states for this compound. So, fortunately, we obtained qualitatively the same result for all the superconducting states. So therefore, I'd like to just show you the most simple case, the isotropic case with superconductivity. So then the here, okay, so yeah, so this figure shows the temperature dependence of the superfluid weight in the model, and so the difference of these two lines are so contribution from the quantum geometry to the superfluid weight. So according to these results, we conclude that the almost half of the superfluid weight in these systems comes from the quantum geometries, and the BT transition temperature is enhanced to approximately 10 Kelvin in these systems. So the quantum metric is important for the high temperature superconductivity in this system. Okay, so maybe the time is up. Oh, I see. So, okay, thank you very much. Okay, so almost the time is up. So I'd like to just show you the flash of the third part of my talk. So, we studied the superfluid weight, and it is also related to the stability of the FFL superconducting state with finite momentum of group pairs, because the superfluid weight is a phase stiffness, and it is equivalent to the second order derivative of the free energy with respect to the momentums. So the question is the following. The question is the following. So can we stabilize the FFL superconductivities by using the quantum geometry? So, but it is impossible according to the theory by social Pelton and Professor Telmas, because they showed the topological band. So that means the quantum geometry correction to the superfluid weight must be positive. But so this is the case of the SLS superconductors. And so yes, we noticed that we found that we have a chance to obtain the negative superfluid weight by quantum geometry in unconventional superconductors. And actually, so this is the case. Phase 2 band has the sorry, the pair potentially changes the sign between the two bands. So we demonstrated these possibilities by solving the so-called Gauss model proposed for the iron-based superconductors. Okay, so in this case, yeah, we see the quantum geometry induced FFL superconductivity. Probably, so this is a route to the flat band Cartesian state as proposed by Chen and Wilfan. Okay, I'm sorry, the time is up. So this is a summary of my talk. So thank you very much for your kind attention.
So is it okay to take questions from the Dejan node first?
First question, okay.
Yeah, so yeah, please.
Yeah. We have questions.
I'd like to ask you about this. Sorry, quantum geometry. Do you mean, for example, if you have appearance of quantum geometry in the system, is it mean strong localization limit for the electrons? Are they equivalent, for example?
No, so as discussed by previous speaker, Professor Rowe, the quantum metric, due to the quantum metrics, the electrons become delocalized. So electrons are not localized in the systems.
You have strong localization limit or delocalization limit.
Yeah, quantum metric causes the delocalization in general.
But in this case, why you have superconductivity? Because superconductivity means strong localization for the electrons also.
Strong localization in superconductors. I'm sorry, maybe I don't understand your question. So positive means a localization.
You have here quantum geometry. It means the quantum confinement for the electrons. Yes.
Quantum confinement.
Sorry.
Yeah. So usually the So due to the role of the quantum metrics, the confinement of the electron wave functions is suppressed. So the electron becomes more itinerant, so due to the quantum metrics.
That's more itinerant.
Yeah, in many cases. So, so this is not the case for the Cooper pairs. In some cases, so that is the reason why the effect of superconductivity can be stabilized in some cases for superconductors. So that is a counterintuitive result.
So, okay, let me take one question here. Okay, Taejeon, we have one question from here. Okay, please.
Yeah, thank you for the nice talk. I wondered, sorry, it's not your topic, but you said the quantum metric is very important. So that I wondered, please have some advice that if we consider the vortex stage in the iron selenide, do you have any insight how this the quantum metric affects the vortex stage? For example, the discrete levels or the Majorana bound states. Any comments on?
So I suppose that quantum metrics plays a role for the particle bound state in the vortex format. So maybe you know that the very curvature plays a role. So it has changed the position of the bound state in the superconducting vortices. So in the same way, in a similar way, so I expect that the quantum metrics change the kinetic spectrum of the particle bound state. But as far as I know, so no one has calculated the contribution to the particle bound state.
So you think we need to take into account this quantum metric effect in their boundary condition?
Yeah, I think so. So Professor Rowe has demonstrated that the quantum metric is important for the length scale of the bound state. So I suppose that the similar phenomena should apply the vortex for other.
Should affect the vortex size. So it will also affect the engine.
Thank you.
Okay, so I think we can move on.
Yeah, let's wait to speak again.